Hello again and welcome to the second video in the pre-lab series for your college General Chemistry 1 laboratory. Today we're going to be talking about the density measurements or density calculations part 1 exercise. I'm going to run you through some of the equipment that you'll be using that might be new to you in some cases depending on your previous chemistry experience. And again, as part of the pre-lab lecture, I'll go through the pre-lab questions that appear in your laboratory manual to sort of reward you for tuning in today. All right? So the main goal of our exercise today will be to calculate the density of several objects. Density, of course, is a ratio of an object or substance's mass to its volume. Actually, I've just answered question 1 in the pre-lab for you. There you go. So what we need is the ability to measure these two properties then, mass and volume. Mass is very easily taken care of in our lab using an electronic balance. So it takes care of all of the issues of sig figs for you. We talked about significant figures both in last week's lab, but also in lecture you've addressed the issues of significant figures now. I do want to make sure you understand that when your balance reports a mass, maybe 5.621 grams, that you record all 4 of those significant figures. And it should be no different if this was 5.620. The exact same balance has been used. Therefore, the number of significant figures should not change. And this 0 is quite important. Please don't drop it off and write just 5.62. So that's sort of my plead for your significant figures relating to mass. Now, volume can be measured and calculated in a variety of different ways. In today's exercise, we'll most often be using displacement of volume to come up with the volumes that we measure. So we have a couple of instruments and measuring devices right here to look at. The first is the graduated cylinder. Graduation are just markings along the cylinder. That's what graduated means. Okay? Just as a little bit of information for you, the greater the number of markings, and by that I mean in terms of showing the whole unit, the tenths of the unit, the hundredths of the unit, the more expensive the piece of glassware is becoming. The more accuracy you have, in other words, the greater the cost of that instrument. Always keep that in mind when you're handling these objects in the lab, lest you break something that might be very expensive. Of the two pieces that I have here, the graduated cylinder is marked off in terms of whole milliliters. So the markings, there are large markings every 10, but it does show us the individual 1 units. Okay? So this is our graduated cylinder. We'll read the volume of the graduated cylinder from the bottom up and to the bottom of what's called the meniscus. Liquids, almost all liquids, mercury would be one of the few exceptions, but since we usually work with water or water-based liquids, they form a meniscus that is downward shaped. And so you want to read from the bottom of that meniscus. Now, our correct rules for measurement would mean we record all of the known places of certainty plus 1 guess where we mentally divide. So I want to mentally come over here and see that I'm certain of 1, 2, 3, 4, 5, 6, 7, 8, and I am charged using good measurement practices to mentally divide the distance between 8 and 9 into 10 parts and to estimate how high or low the bottom of that meniscus falls. So a fair guess would be 8.1, 8.2, 8.0. All are reasonable guesses for this volume, I would say. What's important is that this digit shows up as part of your measurement. To just say 8 is an improper application of the scale that literally we've paid for on that piece of glassware. The other device that we have for measuring volumes is a burette. And a burette has more markings of accuracy than our graduated cylinder does. Our burettes in our general chemistry lab are marked to the tenths of a milliliter. And so I won't show the whole burette, but the markings now actually count downwards. All right? So 0 is at the top of the burette, and then you would count down from there. And because the tenths are now shown, we're going to estimate to the 100th place when we use our burette. We again read the bottom of our meniscus. But we read down with a burette. So while this number falls between 1 and 2, in the graduated cylinder we read from the bottom up. And so we would say this was 2 point something. But with our burette, we read from the top down. And this is 1 point, let's see, 1, 2, 3, 4. Those are the known certain places. And again, estimate between the 1.4 and the 1.5 how many tenths of that you believe the meniscus ends at. So maybe 1.42, 1.43. You should always, on a burette reading, in your York College Chemistry Lab, have 2 digits. Understand? Because ours have those tenths marked, so you should always be estimating the 100th place. Okay. And again, a fair reading would be 1.43. That last one is up to interpretation. Okay. So that would be our graduated cylinder and our burette. In the graduated cylinder, today in the lab, you will at one point drop objects into the graduated cylinder and the volume will increase in the liquid. The difference between the volume 1 and volume 2 is the volume of the object that you've added into the graduated cylinder. With the burette, it's always a relative value. Students often want to fill the burette to 0 at the start and work very hard to get the meniscus on 0.00. And that's actually not necessary, because now I can simply record my starting volume, pour out any amount, and record the new volume, and simply subtract the 2 to come up with the volume that has been dispensed from the burette. And that will be part of your exercise today as well, to dispense certain volumes, and then you'll weigh them to come up with the densities of liquids. The mass of that liquid divided by its volume will be how you'll calculate its density. One of the other techniques that you'll use today for calculating density will be the method of displaced mass. And I want to explain briefly that how you'll approach this problem. You're going to attempt to solve for the density of a rubber stopper. And so again, the density of your rubber stopper means having its mass and its volume. We can easily get the mass of the rubber stopper from the balance. To get the most accurate volume, we're going to use what's called displaced mass. And we will use a small Erlenmeyer flask with a stopper in it, a lid, a glass stopper in it, to create what we call a pycnometer. In chemistry, a pycnometer is simply a device with a known volume, or an instrument with a known volume. And here the key is precision, how precisely we know that volume. We will get this volume from the density of water. We will fill the pycnometer completely with water, weigh it to determine the mass of the water, and then use the density of water to calculate the volume. Okay? So filled with H2O, you will find the mass of H2O and then use the density equation to get the volume. The volume would be the mass divided by the density. You will look up the density of your water for its given temperature, because the density does slightly change with temperature. There's a link to a table, that's the quickest way, I would say, to an online table of densities and how it varies with temperature. Now, let me draw a picture that is in your laboratory manual and explain it. It looks like a seesaw, but it's a very simple demonstration of what we're doing in the lab. So imagine we have our pycnometer filled with water, and we have a rubber stopper. Okay. Combined, we have the weights or masses of these two objects. And so, let me give us a number. Let's say their combined total mass was 58.213 grams. It's just a totally arbitrary number. Okay. Now, if I take that stopper and insert it into the pycnometer, just as if I dropped an object into this graduated cylinder, the level of the water will rise. Unfortunately, this is already filled with water. So what's going to happen is the water would overflow, or some of it will come out. If we did that on the balance, directly on the balance though, there would be no change in our total mass as long as we collected that little bit of water that splashed out. This side here should still be 58.213 grams. But now, okay, because we won't have this little bit of water, we can solve for what mass of water was displaced. Here we have H2O plus the stopper equals the total system, if you want to call it, okay? The combo plus the displaced water. Because this is balanced, I was able to put an equal sign in. And it should be very easy to simply subtract the combo mass to come up with the mass of displaced water. Once you have the mass of displaced water, you have its volume, again, based on the density equation here. So you take that mass, turn it into a volume. Not only is that the volume of water that was displaced, but why was this much water displaced? Because of the rubber stopper that you added. Therefore, this volume also equals the volume of the stopper that you've put in there. Now you have the mass of a stopper and its volume via the displaced mass of water. Therefore, you have what we believe will be the most accurate accurate means of determining the density of that rubber stopper. You'll calculate that same density a different way simply by displacing volume directly in your graduated cylinder. But because of the markings on the graduated cylinder, you're going to have fewer significant figures, fewer decimal places in your volume. Therefore, your answer is less accurate. There's less precision in the decimal places that you would have. Okay? So that's the heart of what we're doing in lab today. Let me turn to the other two pre-lab questions that are remaining. I've already answered question 1. This is our formula for the density. Second question says, well, what are the standard units? All we need to do are apply the standard units for mass, which would be the kilogram, and for volume, while we measure it, practically speaking, in a variety of other ways, milliliters today, and that might be converted to centimeters cubed, the standard unit would be meters cubed. Although this is the standard unit, again, you will come across many other units for volume, for density. Grams per milliliter is one of the most common ones. So the third question then says, let's calculate the density of an object. We're given its mass from the electronic balance, 35.804 grams. And we're told that the volume by our displacement method is 8.52 milliliters. So the density is quickly found by dividing the mass by that volume, or 4.20 grams per milliliter. And here I have applied the rules of significant figures. This value has 3, this value has 5. When we have a quotient or division, our answer can have only as many figures as the value with the fewest significant figures. Thus, we round, even though this might have more digits on our calculator or in a spreadsheet, we must round it to 3 significant figures, 4.20. And don't forget units. They are always an important part of your answer as well. With that, I'll wrap it up for today, and I wish you good luck in calculating the density of your various objects. Again, enjoy the lab. Make sure you're taking good notes, as you will return to some of these concepts for your laboratory exam at the end of the semester. Have a good one.